Hey, hello everyone. So, yeah, hold on. All right, probably not a surprise at this point, but I did just get back from a run. Um, yeah, how are y'all doing? Uh, this is the regular twice weekly study session. Yeah, so if you remember, or if you've never been here before, so my name is Aaron. I am a data scientist currently with government, and I am doing these twice weekly study sessions to kind of force myself to study some stuff, and either refine or learn new skills, just to become better at my job, and also just be able to do more interesting things, and help understand some of the stuff that I use on a day-to-day basis. Um, and the current project I'm working on right now is actually trying to convert the Introduction to Statistical Learning book into Python, because it's actually based in R. And I'm picking this one because it's a little bit easier to pick up than the Elements of Statistical Learning. Both are free, both are excellent. It's just that Elements is more like a reference textbook, kind of like if you need a dictionary, then you go to Elements. But if you just want to have an understanding of statistical learning, machine learning, that kind of stuff, Introduction is totally fine. Um, so yeah, I keep saying that off stream I will work on these things, and maybe make them coding streams, and then I never have time to actually do a coding stream, which is unfortunate. Um, so yeah, I think one thing that I should work out for myself is actually make out a designated schedule for streaming, just like I have with these study sessions. Although, frankly, I keep saying like I'll start at 3 or 4 o'clock, and then I usually start at like 4:30. Um, so yeah, that's on me to be a better, I guess, content creator or something, and just make this project a little bit more real, I think. So today, what I'm going to do is actually start going through the chapter 2 exercises. And this is going to be kind of like an actual study session, right? Like these are actual problems to do. So you can't see it, but I'm actually in terminal, and then I'm going to go into the directory, uh, and get things set up. In the meantime, how are all of you doing? Love to see in the chat what y'all are working on, any progress on the things that you're studying, etc., etc. Yeah. Okay, I've got Visual Studio Code open. I have got a notebook for the what's it called? For the exercises, and I think actually today might be better to just split screen evenly, and then maybe I'll get like a hand camera or something after. Oh, actually, I've got now this I had gotten this like Elgato, like this Elgato Camlink, um, to use with my work laptop. Um, Actually, no, to use with my actual laptop, and then it became like a work laptop webcam. I don't need it for work, so maybe I will actually just hook it up to my desktop and then use this as like a hand camera. Yeah, look at that, figuring out alternate uses for things that mm, maybe didn't have to spend money on. Yeah. Okay. So what are we gonna do? We are going to organize some stuff and get my notebook out so that I can actually try to solve these problems. And then when it comes to the coding section, I'll head back over there. And I think I'm going to work through these by hand, just because I kind of worked a little bit better that way. And then later on, I'll probably convert the solutions into a notebook file or a markdown file. Yeah. Okay, so first things to do. I have in my notebook here that there's a section for the lab, and I'm just going to write check git repo for notebook file. And then we're going to move to, that was easy, chapter 2.3 done. 2.4 exercises. It's a bold move. I'm doing this in pen. Conceptual. As you can see on the... Actually, can you see? Let me look. Yeah, I think you can see that in the stream, right? If not, I will make that a little bit bigger. Yeah, that looks fine. If anything, I can get rid of this thing on the side. Guess I don't really need that thing on the left, or as much of it. There you go. And then maybe zoom in some more. Cool. That looks good, right? Yeah, like y'all can actually read that. So yeah, okay, so conceptual. So we've got number 1 for each of parts A through D. Indicate, I guess I don't need to write solutions because there should actually be solutions for this. Whether we would generally expect the performance of a flexible... Oh, also kind of funny, you can probably see on the stream, I got a monitor. It is my brother's old monitor, and there are no power cables because in organizing our place, I put all this stuff together. So there's no power cable in the box, and then also this is DVI and VGA, and I have no, I thought it was here. I couldn't find my display port to DVI cable, so this thing is totally useless right now, but it is actually, well, not totally useless, so it's helping me figure out where I want my monitor, and I think I don't want it here because little vein thing, it does hide my desktop, and when I'm standing, it hides my amoeba collection, so I think I actually want to put it under where the webcam is right now, so yeah, and I will probably just buy a monitor soon. Yeah, so next paycheck, I think. Okay, expect the performance of a flexible statistical learning method. To be better or worse than an inflexible method. Justify your answer. Okay, so for A, sample size n is extremely large and the number of predictors is small. Okay, in this case, I would say that the inflexible method would be better because we've got so many samples and then a small number of predictors. We don't run into the cursive dimensionality that can happen with like very flexible methods. So I am going to guess, hold on, is my... I'm going to guess that flexible would be worse. Um, so I'm going to say flexible worse. And then I'm going to try to find solutions. Introduction to statistical learning. So I'm looking at their they actually do have Jupyter Notebook files for the labs, but they are still written in R, so I don't really know what the differences between the R Markdown and Jupyter Notebook files are. But yeah, so they're not actually written in Python still. And yeah, occasionally I forget that Jupyter, I believe, stands for Julia Python um, R as like the coding languages that are supported. Okay, let's see. Ah, interesting. Okay, so there is, I think unless you pay for the class, there's no official learning set. I'm looking at their discussion forum, and Daniela said like, "Oh yeah, we don't have an official learning set, solution set." Um, so yeah, that's interesting. I found there's like one person in the comments put like, "Oh, here's my unofficial solutions for the work," but there's not that many chapters included. So this author is saying that with more data, the zero mean error should itself play a smaller part in the overall estimate, as you're taking a larger sample of the error distribution as well, which should tend to zero. Thus, the tendency for a flexible method to overlearn would be diminished. Um, so that kind of implies solution. The implication is that flexible is better. I don't know. I don't feel like that actually is an answer. Okay, B. The number of predictors P is extremely large, and the number of observations is small. If you Okay, so the number of predictors P is extremely large, and the number of observations is small. In this case, I think it's really easy to pick up on noise in the data because there's obviously so many predictors. So in this case, I would say that the flexible is worse. Actually, for A, I think it makes sense that the flexible is better because you can keep sampling or you can keep trying to fit your method, and there's just like you just have a lot of data to work with. So it's kind of the opposite of this of B, right? So with B, your algorithm or whatever can pick maybe even the wrong predictors and just capture a bunch of noise. But with A, it's not likely to be the case. Let's see the solution. Yeah, their solution. Almost guaranteed, it says, to overfit data. So inflexible is better. C. I would say, oh wait, flexible is worse here. Easy to capture noise with a lot of predictors. I think for A, flexible, maybe not worse, is like, I would say, okay, so flexible is better, opposite of B. But I kind of wonder if, like, is there, well, okay, all we're being asked is it better or worse? So let's just say that. So with C, the relationship between the predictors and response is highly nonlinear. The relationship between predictors response is highly nonlinear. It kind of seems like this is maybe an obvious situation where the flexible is going to be better. Yeah, just because like if it's more flexible, it can adapt to the situation. I'm looking at the solution now, and it says highly nonlinear responses require more flexible learning methods. Inflexible methods won't be able to adapt appropriately and will result in a high bias term. So flexible. Oh, whoops, I should say flexible better. Better. Reduce lower bias. And the solution, flexible is better. For adaptability. D, the variance of the error terms is extremely high. Well, that's pretty obvious. Variance of the error terms is extremely high. And this is phrased very obviously because like C and D talk about the bias variance trade-off. So with the more flexible methods, you trade your variance you trade your bias for higher variance. But yeah, so in this case, like if the variance is extremely high, then that says that the flexible is worse. So the solution says an inflexible method will be better as the high variance in the error terms will make a flexible method overfit the data. Inflexible Oh, I should say flexible is worse due to high variance penalty. Inflexible, so solution says inflexible is better. High variance in error terms will make, not bake, make flexible method overfit. Okay, number 2. Explain whether each scenario is a classification or regression problem and indicate whether we are most interested in inference or prediction. Finally, provide N and P. Okay, so we'll say classification or prediction. Sorry, classification or regression. Then inference or prediction. Then what are N and P? Okay, so A, we collect a set of data from the top 500 firms in the US. For each firm, we record profit, number of employees, industry, and the CEO salary. We are interested in understanding which factors affect CEO salary. So in this case, I would say it is, okay, hold on. We have data about profit, number of employees, industry, and CEO salary. What factors affect CEO salary? I think that this is a regression problem, and we are interested in inference because we're not really looking for, it's kind of weird. We're like looking at trying to get the CEO salary, but that's not actually what we care about, right? Like we want to just see what the, what variables, I guess, have a significant coefficient. Yeah, so to me, I feel like that is more about inference than prediction. And then N and P, so we have 500 firms is your N, and P would be profit, number of employees, industry, so 3. I was a little confused because I was like, wait, are they talking about like probability or? So let's say I say that this is a regression. Looking at inference. And we have N equals 500, P equals 3. Profit, employees, industry. Although this is, because industry is categorical, once you one-hot encode it, it may turn into something else. So maybe that part is a bit of a trick question. Let's see. And the solutions say regression, yay. Inference, yay. N equals 500. P equals 3. Hey, cool, cool, cool. All right. Okay, so for B, we're considering launching a new product and we wish to know whether it will be a success or failure. We collect data on 20 similar products that were previously launched. Each product we've recorded whether it was a success or failure, price charged for the product, marketing budget, competition price, and 10 other variables. Okay, so we have launching new product, want to know success or failure. Have data on 20 similar products. Data has, let's see, success failure, so S/F, price charged, marketing budget, competition price, uh, 10 other variables. Okay, so in this case, I think we are trying to do classification with prediction, because we actually want to know the result. And our n equals 20. Our p equals, we have 10 variables, and then in addition to those 10, we have competition price, marketing budget, price charged, so 13, because the success or failure is the dependent variable, and I would not count that as part of the things we're trying to look at. Okay, so the solutions say classification, prediction, n equals 20, p equals 13, so cool, got that one. C, we are interested in predicting the percent change in the US dollar to euro exchange rate in addition to the weekly changes in the world stock markets. Hence, we collect weekly data for all of 2012. For each week, we record the percent change in the currency, percent change in the US market, percent change in the British market, and then percent change in the German market. Okay, so predicting percent change in USD euro exchange rate. Ooh, sorry. Weekly data from 2012, percent change in USD euro, percent change USD US market, percent change British, and percent change German. So in this case, we are looking at, I think, regression, because we're trying to calculate the percent change. And then prediction, n equals 52 because it's weekly data. And then P equals percent change in the US market, percent change in the British market, percent change in the German market. So P equals 3. That's what I would say. So solutions, we've got regression, prediction, n equals 52, and P equals 3. Cool. All right, next one. 3. So we revisit bias variance decomposition, provide a sketch typical of squared bias, variance, training error, test error, and Bayes or irreducible error curves. Oh my gosh, I'm sorry. As we go from less flexible statistical learning methods towards more flexible approaches, the x-axis should represent the amount of flexibility in the method, and the y-axis should represent the values for each curve. There should be 5 curves. Be sure to label each one. Okay. Okay, so draw xy axis. We want squared bias, variance, training error, test error, Bayes, irreducible error curves. Okay, so x is degree of complexity, I guess, of method complexity. And then y-axis is error. So, oh gosh, sorry. Well, we know that the more flexible methods have lower bias. What would the shape be? If it's squared, won't ever approach 0. I would think that maybe it's like asymptotic. So I'm going to try to draw that. Bias, BN, bias squared. And then the variance, I would say, is like the other way. So you start with low variance, and then it just keeps getting bigger and bigger. So that's variance. Training error. Training error should start out pretty high and then continue to go down. And then test error. This is a test error. Well, it kind of depends, right? Like if you start overfitting, then the test error would go back up. So in an ideal case, test error would also go down, but I think it's more realistic to assume that your test error is typically going to start higher, and then it will decrease as your models get more complex. But I think even in a best case scenario, you start, you'll never get as low as the training error. And let's see, it might, as you get more and more complex, I would draw that starting to go up again, because you never know, right? You may be overfitting. But I think also there's just and this may factor in with the Bayes or the irreducible error, your best case scenario. Actually, I don't even remember what the Bayes plot will look like. Okay, so let's see. The squared bias does go down like I drew. The variance actually goes up like I drew. Cool. The training error basically followed the bias, which is kind of what I drew too. The test error uh, goes, oh yeah, okay, cool. So yeah, this is exactly what I said. The test error is supposed to go, let's see. And then I forgot that the Bayes error is just like a flat line. So that was something I forgot. I was like, that's supposed to be your best case scenario. So what exactly does that look like? So I'll say the solution has essentially what I drew for a few things. So bias, variance, then training, your test, and then Bayes. Okay, cool. Explain why each of the 5 curves has the shape displayed in part A. So B. You expect squared bias to go down. Man, I keep writing BN. Goes down asymptotically with complexity. Variance goes up. I'm not sure why I gave it like a almost like a quadratic shape, like half of a quadratic shape. I think because I mean this plot is squared, I believe. Yeah. Training should go down test will go back up with model complexity and Bayes represents best case scenario. Or what do they say in the solutions? Bias is the result of the mathematical form of the training model not being matched the underlying mathematical reality of the system being studied. Generally speaking, the more flexible the training model is, the more likely it is to match the mathematical form of the system in question. Yeah, that is a good answer. So let's see. Bias is a result of the mathematical form of the, and I think that's actually exactly what they say in the lesson. Form of the training model not being matched to the underlying mathematical reality of the data. Reality of the system being studied. Generally speaking, flexible the training model is the more likely it is to match the mathematical form of the system in question. Variance refers to the change in our estimate of the systematic information function f hat when we use different sets of training data. It is minimal when flexibility is minimal. As expected. When more flexibility is introduced, variance will change as the learning method will be able to adapt to points easier as it has more degrees of freedom. Training error. I don't know why this person wrote training and test error out of order. Training error is reduced as more flexibility is introduced. As due to the tendency for the model to incorporate the error in each point into its estimate. Test error is minimal at the point where flexibility most closely matches underlying mathematical form of the system. Test error can never be below Bayes error. Bayes how many S's are in Bayes? One. That's okay. I think it's just one. I think they're the authors of the book are forgetting one apostrophe. There is no apostrophe. Okay. It's just Bayes. Bayes error. In the solution, there's an apostrophe. So I was like, wait a minute, isn't it named after a person? Is an irreducible constant that exists with no relation to the choice of learning model. Okay, let me check on something real fast. Okay, we've been streaming for 48 minutes. Okay, so that was number 3. All right, 4. You will now think of some real-life applications for statistical learning. Describe 3 real-life applications in which classification might be useful. Describe the response as well as the predictors. Is the goal of each application inference or prediction? Explain your answer. This is pretty open-ended. So I don't know. Describe 3 real-life applications. Well, let's see. We want to name cuisines. And the response would be a classification, like what type of cuisine the food is from. The predictors could be the ingredients, could be the instructions or the steps to make the food. Let's see. Okay, so that's 1. We could do... and that would be prediction. Oh, that's an interesting... we could try to, let's see. Actually, I have a lot of project ideas for prediction. I wanted to actually do a thing that like compared, I must have dropped something or scratched my table. I think another one would be, I was curious about, YouTube reviews and general tech reviews for stuff because I feel like I have read several reviews where I don't know what the difference is between the review itself and then the press release is issued by the company, specifically with Apple products. So I wanted to build a thing that was like, oh, okay, we'll just compare the text of the press release or the announcement with the review and judge the similarity and then determine whether or not this is actually worth someone's time to read, or like at least how similar the different things are. And then you can kind of pick and choose, like maybe you have an author or a journalist or reviewer that you really like, and there's so many that are so similar that it's not worth trying to get like 3 different views. So yeah, I think that would be it. I think that depends, right? Like if if you're trying to judge whether or not it is worth reading a particular author's contributions, then that is a predictor. But if you just care about how they are related to each other, I believe that would be inference. Um, and then I think another one would be, let's see, where would we classify stuff? We could do I'm trying to pick things that I scrolled down a little too far in the solutions, so I see two solutions right there, and I just don't want to read those. Um, yeah, let's see, prediction. We could try to do, maybe we can try to uh, pick and choose what we could do, maybe like sentiment analysis on text. Given the text that's, I really like NLP, so that's kind of why like stuff projects I come up with are NLP related. Like whether or not something is positive or negative, like that's the really obvious stuff, or like whether or not it could be hurtful to someone. So that could be classification, and then that would be prediction. But if we're curious about what words are involved, then that would also possibly be inference, I think. Okay, so real life applications in which regression might be useful. So very obvious one is predicting the value of prices, or the prices of houses. So then that would be, this could give you a number at the end as the response, and the predictors could be like location, number of rooms, number of bathrooms, square footage, etc. That would be, I think, prediction more than anything. Let's see, other things for regression. I kind of want to look at the problems that we did before. We could try to do stock. I guess given the like things like profit, and I think actually like, it could be a classification thing. Like, do you think this is worth buying as a stock? But for regression, like maybe the value of a stock given the quarterly performance, I guess number of currently issued shares or something, what week it is, whether or not there's like recent announcement, cash on hand, the kind of stuff. So that would be a prediction. And let's see. Another regression one could be also, you probably noticed I moved my mic in because it was driving me crazy on the other side. Now it kind of drives me crazy on this side because the headphone holder is kind of right where I would be walking if I'm using my treadmill. Yeah, but I was a little worried that like it might be a little distracting coming out from this side instead. It looks like honestly it's fine. Yeah. Let's see. So describe. Okay, so one more application for regression. So this is something where we care about numbers at the end of it. Maybe we could do something like ideal number of students in a class, given the like county size or district size, income level, access to various resources. Yeah. Describe 3 real-life applications where cluster analysis might be useful. Let's see. So actually, if this is kind of like similarity analysis, then in this case, like that, the previous project I mentioned where like, oh, if these words are too similar, then maybe these are, this is like not worth reading as a separate thing. So that could be one. And in that case, like maybe that's not really appropriate for a class for inference classification. Another one would be like if you're trying to figure out who is likely to buy something, you can base it off like, I guess, other demographic data. Um, and then what else? Maybe the kinds of things that will sell in addition to like unlike like who's going to buy something. So like given like some toys like my amiibo here, what are the characteristics that are helping things like let's say the Pikachu one, that was really obvious. The Pikachu amiibo sell hot versus like maybe the Fire Emblem one doesn't sell as hot, right? Yeah. Okay, so I don't really feel like writing all those down because it's more kind of discussion based. 5. What are the advantages and disadvantages for a flexible versus less flexible approach for regression or classification? Under what circumstances might a more flexible approach be preferred to a less flexible approach? When might a less flexible approach be preferred? So let's see, number 4 is open-ended discussion. Of classification, regression, cluster analysis. And then for both classification, regression, inference, or prediction. 5, flexible versus inflexible. Let's see. For regression or classification. So for regression, if the data is strongly nonlinear, then a more flexible model should be better and would fit like the nuances of the system a little bit better. I guess same with classification. A less flexible approach might be when we've got like when there's just tons of data. So when there's tons of variables to predict and the variance starts risking becoming quite high. Let's see. Yeah, okay, so the solutions have a table. It's like it's like advantages, disadvantages, more flexible, less flexible. Advantages are for more flexible advantages, better for highly nonlinear relationships. Disadvantages, more difficult to compute. I didn't think about that one. And can overfit the data. Incorporating irreducible error into the model. Less flexible is easy to compute, minimal variation. Disadvantages cannot fit nonlinear data adequately. So yeah, especially the compute time. That's actually a very good point to discuss. Normally, I kind of like ingrain that of like, oh, you just start with the simplest and then you move on. But like that is actually a distinction to keep in mind. Okay, so 6, describe the differences between a parametric and non-parametric statistical learning approach. Okay, yeah, ooh, sorry about that. I just got like a cough. Describe the differences between a parametric and non-parametric statistical learning approach. What are the advantages of a parametric approach to regression or classification as opposed to non-parametric? What are its disadvantages? I kind of forget what a parametric and non-parametric statistical learning approach is, so I'm just going to skip straight to the solution. So parametric advantages, problem reduced to predicting a set of parameters for f. Disadvantages, assuming a form for f can restrict the accuracy of the generated model, aka high bias, low variance. Non-parametric is no form of assumption taken for f, so same process can be used to fit highly varied and nonlinear sets of data. It's very difficult to compute in comparison to a parametric model. Need a greater number of observations to generate a good model. So the feedback for me is to go back and review the parametric versus non-parametric approaches, because I don't remember what these are. Because like I know conceptually it's like, oh, there's one uses parameters and one doesn't, but I'm like, what does that actually mean? Like, are you actually assigning the variables or the coefficients to the variables, or you're assigning something like a learning rate, like with hyperparameters? So let's see, parametric versus non-parametric approaches need to review. Okay, 7. The table below provides a training dataset containing 6 observations, 3 predictors, and 1 qualitative response variable. Suppose that we wish to use this data to make a prediction for y when x1 equals x2 equals x3 all equals 0, using k nearest neighbors. Compute the Euclidean distance between each observation and the test point x1 equals x2 equals x3. Okay, so that's going to be a little annoying. All right, so we've got 6 observations. X1, X2, X3, and then Y. So we've got 1, 2, 3, 4, 5, 6. 0, 2, 0, 0, minus 1, 1. 3, 0, 1, 1, 0, 1, 0, 0, 3, 2, 1, 1. Red, green, red, 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 green, green, red. Okay, so test point. 0, 0, 0. Okay, so now we're going to find the, oh man, this is going to be tedious. So Euclidean distance is just the distance between the square root of the square root of the sum of squared distances from each point. So that means, so A, Euclidean distance calc. So there'd be test, then obs 1. So that's square root of 0 minus 0 squared plus 3 minus 0 squared plus 0 minus 0 squared. So that is going to be 3 because there are 2 zeros. So actually this would be obs minus test, I guess. Yeah, obs 1 minus test. So then we have obs 2 minus test. And that's square root of 2 minus 0 squared plus 0 minus 0 squared plus 0 minus 0 squared. That's square root of all that. So that's 2. 3 minus test. Square root of 0 minus 0 squared plus 1 minus 0 squared plus 3 minus 0 squared. So that's 9. So 0, 1, so square root of 10. It's 10. 4 minus test. Square root of 4 is 0 minus 0 squared plus 1 minus 0 squared plus 2 minus 0 squared, and that's going to be 4, 5. So square root of 5. 5 minus test. So that's minus 1 minus 0 squared plus 0 minus 0 squared plus 1 minus 0 squared. So that's square root of 2. 6 minus test. So that is square root of 1 minus 0 squared plus 1 minus 0 squared plus 1 minus 0 squared. And that is equals to square root of 3. 3, 2, root 10, root 5, root 2, root 3. Cool. All right, I got that right. B, what is our prediction with k equals 1? Why? K equals 1. And then the prediction is, well, the shortest distance is, the nearest neighbor is, let's see, so nearest neighbor is, square root of 2 is 1.4. So that would be observation 5. So that would mean that the prediction is green, because root 2 is the smallest. Cool. So that is correct according to the unofficial solution. So k equals 3. Well, the 3 nearest neighbors are observation 5, because it's 1.4, and then observation 6, because that's root 3, which is 1.7, and then observation 2, which is 2. So it'd be obs 5, obs 6, and then obs 2. So that's green, red, red. So the majority says it's red. Yep, cool. And then D, if the Bayes decision boundary in this problem is highly nonlinear, then what would we expect the best value for k? Then would we expect the best value for k to be large or small, and why? If it's highly nonlinear, I would expect the best value for k to be small, because that would allow for the greatest flexibility. So if Bayes decision boundary is highly nonlinear, I expect small k to be better to allow for more flexibility. Unofficial solution says small k is better for highly nonlinear decision boundaries, including less items than the nearest neighbor calculations means there's less overlap of observations used among varying points, allowing subsequent points to vary more rapidly in their decision predictions. Okay, cool. So that was number 7. 8. Oh, this is the time where it goes into the lab. Let me see, are the rest of these in? Yes, okay, so there's 3 more problems, and they're all in the applied in, I would use it in a Jupyter notebook. So I think what I'm going to do, because I think I actually need to have a short stream today, I'm going to power through, not take a break, because now we're actually doing code, and it's very different from writing stuff in the notes. So I'll write 8 through 10, or actually applied. So 8 through 10. Excuse me. Glad I muted. Hope I muted. Hope the mute button actually worked. 8 through 10 are in the chapter 2.4 notebook file. File, not files. Yeah, okay, cool. So, now we are going to switch over to coding session, minimize OBS. So I wrote this notebook file last time, and what we're going to do now is basically for number 8, change cell to markdown. So this would be problem number 8, and this uses college data. CSV. Insert code cell below. So we're going to do import pandas as PD. Oh, I didn't. That doesn't make any sense. Didn't I do poetry? Poetry shell. Yeah, okay. Whatever. Select kernel. We're going to do Python 3.8. Why are you doing this to me? Which Python pandas can I do IPython? Cool. Import pandas as PD. Which can I do PD dot version? I don't think I can. I'm trying to use Python commands inside to define libraries. Which pandas? Yeah, I don't think that's correct. Okay, exit. It's really odd. Poetry is running. Code dot. Should know which kernel I'm using. That's weird. Okay, let's try this again. Yeah, I don't know why I didn't see the .venv. Maybe I just didn't see it. Okay, so college data path equals be a string dot. Let's look at our hierarchy data. Okay, dot slash data. Then in that would be college.csv. So college data frame equals pd.read CSV and be college data path, and then a college data frame dot head, and let's do 10. Cool. I think there might be too many variables and it may not show. Oh no, it did. Okay, cool. All right, so we've got everything listed there as our college information, and then it shows here is the descriptor. Problem statement has the explanation. Well, okay, let's just put this in the change cell to markdown. From the problem statement, the variables are defined as, I don't know if I can just copy paste this in here. Okay, cool. that worked. Okay, well, that formatting didn't work, so I have to do maybe that should fix it. Very cool. Okay. Um, oh, it didn't. It didn't do all of them. All right. Da, 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 da. Okay. I seem to have already done what I normally would do, and it's actually a pretty easy problem. And it is hard to. That's interesting. It's basically just like, oh, just do like a really, really basic EDA on this, and it's like, okay, well, that's pretty easy. There's like, I've already done one other problem. Like, I think two parts A and B are like loaded, and like already done that. Okay. And I think some of the stuff is going to need converting over, but that's what we did before. So I think I will skip this and then make like importing the next one, which is the auto data set. So this can be marked down. So it's 3, 2, problem number 9. And this is uses auto data set from lab. Make sure that the missing values have been removed from the data. Okay, and then the problems are, let's see. And then problem 10, problem number 10 uses Boston housing data set. And then EDA and some plots. And then that is the end of this. So what time is it? 5:42. Okay, I've been going for an hour and 20. Why don't I just like finish one of these? That should not take very long. Okay, so what are we trying to do in the first one? Okay, so let's copy this over. And then I'll add a markdown. So this would be A, and enter. Oops. Okay, so I'm just moving the problem statements into here, and then I will probably just split these up when it's time to answer each of them, each of the questions. So it's a little bit neater and easier to read. Okay. Oops. Actually, like this import pandas as PD, I actually think this should be moved way higher because this is a function that we need. Okay, so it would be why don't I just move this up here, change this thing, import necessary. Get rid of this thing. Okay, so in a comment, I will put what the ask is from the problem statement. So that would be, whoops, that's not what I wanted. Okay, so actually, and similarly, put statement B in here. B, and then can change this into code. And we're going to do C here, which is oh, there's a lot in C. So this might actually just be better copied into Markdown. And then insert cell above. Let's do a code cell above. So one of the things that they ask for in B is you actually want to separate out the first column is just the name of the university. We don't really want R to treat this as data. However, it may be handy to have these names for later. So what we're going to do is I think in pandas I think the equivalent is like to re-index it because like right now the index is the 0, these like integer numbers. But it looks like we can just re-index the data frame to use the college names, which I don't entirely agree with. I'm not sure if every college is actually unique name. But if that is what they want, then that is what we're going to give them, I guess. Okay. I would say that maybe we can do college names data frame equals college data frame unnamed. That's weird. That's interesting. So let's do a code cell. Actually, so let's comment this out. And what I'm going to do is try to figure out what is the list of names of, because like pandas is not seeing this as like, I don't know how this particular first column gets interpreted. Columns. Okay, so unnamed. What the heck? So that first column is literally called unnamed colon 0. So that is an odd quirk. That's bad. Okay, so we are going to take this out, and then I will insert a cell below. The college names are stored in pandas as a column named unnamed colon 0. So therefore, college names data frame. I can't believe it got named that. That's really weird. So we're gonna go with that, and then college data frame equals college data frame dot drop. I'm going to do the same unnamed 0 axis equals 1, then print college names data frame dot head, and print college data frame dot head, and that should actually display like, oh cool, display, yeah, it's cleaned up now. Okay, cool. So that is B. So for C, we want to use the summary function to produce a numerical summary of all the variables in the data set. So that's not true for pandas. In this case, what we actually want to do is the describe function. So that would be let's split this up again so it's C. Okay, so let's do college data frame dot describe. Yeah, okay, so apps accept, so that's all the numerical data, and then we're going to split this up again, and then add a code, then add a markdown. So use the pairs function to produce a scatter plot matrix of the first 10 columns or variables of the data. We want, what did we say pairs was? So we want to do scatter plots. That's contour, indexing, loading data, cleaned up plots. I think plot by default makes scatter plots. Oh no, here we go. PD plot.scatter. Okay, so we are going to do .plot.scatter. This would be college data frame .plot.scatter, and then we need to know the documentation. Well, X and Y. Um, let's look up R pairs plot. Pandas R pairs. Matplotlib. Oh yeah, that's right. It's matplotlib, not pandas. Scatter matrix. Oh, very cool. Okay, so this would be pd.tools.plotting.scatter matrix college data frame alpha equals, I don't even know what the alpha is for actually. That may not exist anymore. Pandas PyData. Pandas documentation. We want to find scatter matrix. And I wonder if that's been deprecated. It's not in tools anymore. Whoops. Let's do fig size. 10. Oh, okay. That's for all of them. Whoops. That's okay. We'll just go with that. So let's insert a code cell. This gets edited again. And then this is C3 PO. So let's see, and then paste. Okay, so use the plot function to produce side-by-side box plots of outstate versus private. So for box plot, so we can do college data frame dot box plot. So in this case, it's asking for outstate versus private. So that tells me like what we actually care about is the column outstate. And then it would be by private. I think that's the notation from, yeah. So yeah, that is that. Let's copy this over again. So we're gonna say, to save some time, we're gonna do this, and we are gonna do this, and then cut that, enter this, code, then markdown, then code, then markdown. So that's the markdown. That's the markdown again, and then we have code. And then let's add a markdown and then add a divider. Okay, so create a new qualitative variable called elite by binning the top 10% variable. We're going to divide the universities into two groups based on whether or not the proportion of students coming from a top 10% of their high school class exceeds 50%. So in this case, so we have to make a custom function. We want to make a new new column based on a condition where college top 10%. Okay. So this would be college data frame, and then new column would be elite, and that's equals college, top 10 perk, greater than, be just 50%, right? Greater than 50 dot. And that should just be a Boolean. So let's say college data frame elite. Cool. Okay, so that creates this like Boolean column, but now we actually are looking for box plot of outstate versus elite. So how can we, that's interesting that this is like not numeric data. Oh, actually, no, that doesn't matter. It's the same box plot as before, right? So you just, we put this in here, and then we do it by elite. There, that was easy. So use the histogram function to produce some histograms with differing number of bins for a few of the quantitative variables. You may find command useful. Divide. Let's see. So what we're actually doing is college data frame.hist. I'm not really sure what else to say. Big size equals. So let's say it's 2020. Let's see. If we use this function, I could try to do a small multiples plot, but I think that would drive me a little bit crazy. But we actually want to control the bins. So bins equals, I don't know. Oh, yeah, I think they're kind of doing small multiples. And then like for each one, you can have a dynamic number of bins, which is already being done. 4 plots can be made simultaneously. Oh, but that's already here, right? Okay, I don't know what to say. So continue exploring the data and provide a brief summary of what you discover. I think that is enough for now. Doing some more EDA would be fun, but that is like a rabbit hole, and it could quickly lead to like, oh, I'm just gonna keep exploring this toy data set. So I don't know. It's already kind of interesting. I have to figure out this. Let's see. The original question stated, excuse me. However, pandas plotting, pandas histogram plotting already dynamically and automatically assigns the number of bins for each variable and plots all of the histograms simultaneously. Yeah. Yeah. So that, I think that is more than enough for now. So let's commit these changes. So git status, make sure everything is actually there. So yep, git add notebooks. Notebooks C2.4 exercises. Git commit. First round working through chapter 2.4 exercises. Solved problem, or actually, let's say we finished exercises by hand in paper notebook. Worked through problem 8 in Jupyter Notebook. And then for a to-do, touch up problem 8 code and references, work through problems 9 and 10. So yeah, I think that will cover it. Git status, git push origin, chapter 2 exercises. Thank you, autocomplete. And that's sent up. So yeah, I think we are actually pretty good. So we've been streaming for like an hour and 40. That's actually longer than I expected to go today, given that I kind of had stuff to do. So yeah, I don't know. I probably was too close to the mic for a little bit, or too close to the screen. I'm sorry about that. Yeah, I don't know. I had fun doing a little work through exercises today. So it was nice to be up here. I swear one day I will actually work through these off camera and then have more stuff to contribute on the actual study sessions and like actually study, because this is really more appropriate for like a working code stream. So yeah, I will do my best to try to work through these and then get back to studying soon. Wait, where's problem 10? Is there no problem? I could have sworn there's a problem 10. Where'd it go? Okay. Yeah, okay, cool. I just have to copy that over. I thought okay, whatever. We'll deal with it later. Yeah, so at the very least, I will see you Thursday for the next study session. Hopefully this will all be done, and then we can actually go back to reading the lecture notes and stuff. Yeah, in the meantime, if you want to reach out and talk to me about the stuff you're studying and your progress, or if you've got any blockers, or if you've got any questions, like I love talking about this kind of stuff and helping people grow. So yeah, until then, it's been fun, and I look forward to the next time we see each other. But yeah, all right, I'll see you all later. Bye.